In this video, we're going to be going over the mathematical method for solving Hess's law equations. So I'm going to start by writing the formula here, and then we'll go through what each piece of the formula means. So this formula is for solving the reaction enthalpy and the standard state. So the standard state is 298 Kelvin and 1 atmosphere. This is done by solving for the sum, so that kind of fancy looking E means sum. The N is the coefficient for a given compound, so the number of moles in the reaction. And the delta FH is the formation enthalpy at the standard state. And these will most likely be found on pages 4 and 5 in your Chem 30 data booklet. So with this formula, we're able to take the total enthalpy of our products and subtract the total enthalpy of our reactants to get the change in enthalpy during the reaction. The first example we're going to go through is determining the combustion of ethanol in an open system. So an open system means that water vapor is going to be produced during the reaction. This is important because water vapor and water liquid have different enthalpies of formation. So our first step in any of these problems is going to be to write a balanced chemical reaction. So ethanol is C2H5OH. I'm going to write it as C2H6O just so it's a little bit easier to balance. So in combustion, we're always combining with oxygen to form carbon dioxide and water. So to balance this, we need 2 CO2s here. We need 3 waters. That gives us a total of 4 plus 3 is 7 oxygens on our product side. We subtract 1 for ethanol. So we need this to equal 6. So we put a 3 in front here. So we have our balanced reaction. Using the information on tables 4 and 5 in our booklet, we're going to look up the enthalpies of formation of each of these molecules or elements. So starting left to right, ethanol has a molar enthalpy of formation of negative 277.6 kilojoules per mole. Oxygen is not in the table. That's because elements have a formation enthalpy of 0. So we don't have to include oxygen in our equation. Carbon dioxide has a formation enthalpy of negative 393.5 kilojoules per mole. And water vapor has a formation enthalpy of negative 241.8 kilojoules per mole. So I'm going to write down our equation here. So our overall reaction enthalpy, delta RH, is going to equal the sum of the coefficients multiplied by the formation enthalpy of our products minus the sum of the coefficients times the formation enthalpy of our reactants. So we're going to start plugging in numbers now. So products first. So we have 2 moles of CO2, and our formation enthalpy is negative 393.5 kilojoules per mole. The moles here will cancel, so we're just left with kilojoules. We're going to add, as it's a sum, 3 moles of water times negative 241.8 kilojoules per mole. So that's the total sum of our products. We're going to subtract our reactants. Now, because water is zero, or sorry, not because oxygen is zero, we don't have to include it. So we're just going to have 1 mole of ethanol times the formation enthalpy of ethanol. And again, we can cancel out our moles. So our final answer should be in kilojoules, and it should be negative 1,234.8 kilojoules. Now the question has asked us to find the molar enthalpy of combustion. So this is not a molar enthalpy yet. We need to look at our balanced reaction. So this enthalpy change corresponds to 1 mole of ethanol. So in the reaction as written, we have 1 mole of ethanol. So in this case, our reaction enthalpy is equal to our molar enthalpy, but it's always important to double check. The next example we're going to look at is the oxidation of iron to oxide. So determine the molar enthalpy of reaction for the oxidation of iron 2 oxide to iron 3 oxide. So iron 2 oxide is FeO, solid. And if it's undergoing oxidation, it's going to react with oxygen to form iron 3 oxide, which is Fe2O3, solid. So we can look up the enthalpies of formation in our booklet. So iron 2 oxide has a molar enthalpy of formation of negative 272.0 kilojoules per mole. Oxygen is an element, so it has a molar enthalpy of formation of 0. And iron 3 oxide has a molar enthalpy of formation of negative 824.2 kilojoules per mole. So we've got to balance this reaction before we can do our Hess's Law math. So we are going to do that by putting a 2 in front of iron 2 oxide, a 4, or iron 3 oxide, a 4 in front of iron 2 oxide, and that should be balanced. So we have 4 irons on both sides and 6 oxygens on both sides. So now we can do our math. So Hess's law states that the enthalpy of reaction is equal to the sum of the products of the coefficients multiplied by the enthalpies of formations of the products minus the sum of the coefficients times the enthalpies of the enthalpy of formation of the reactants. So in this case, our products are just iron 3 oxide, so we'll do 2 moles times negative 824.2 kilojoules per mole. And our reactants are the 4 moles of iron 2 oxide, so 4 moles times negative 272.0 kilojoules per mole. And we can double check our units here, so moles will cancel with moles, leaving us just with kilojoules. And so we're going to get negative 560.4 kilojoules. And the question is asking for the molar enthalpy. So if we look at this, we have 4 moles of iron 2 oxide reacting. So we just need to convert this into molar enthalpy by dividing by the coefficient there. So our enthalpy of reaction is 560.4 kilojoules when we have 4 moles of iron. So we're going to divide by 4. And we get negative 140.1 kilojoules per mole of iron 2 oxide.